Welcome! In this video, we'll tackle the problem maximum number of coins you can get. This interesting problem involves distributing coins among 3 people in a way that maximizes the coins received by one of them. Let's dive in and explore the approaches to solve it. In this problem, we have 3 players, Alice, Bob, and Charlie, who are taking turns choosing piles of coins. There are a total of 3 n piles, where n is a positive integer. Each pile has a certain number of coins, and the players will take turns picking piles until each player has selected exactly n piles. The order of picking is fixed. Alice always goes first, Bob goes second, and Charlie goes last. Alice's goal is to maximize the total number of coins she collects, and the task for us is to determine the maximum number of coins Alice can get if she follows the optimal strategy. The input to the problem is an array of integers representing the number of coins in each pile, and the output should be the maximum number of coins Alice can collect. To understand how this works, let's look at an example. Suppose the input array is piles equals 2, 4, 1, 2, 7, 8. The first step is to sort the piles in descending order of the number of coins, which gives us 8, 7, 4, 2, 2, 1. Now, the game proceeds as follows. In the first round, Alice picks the second largest pile, which is 7. Bob then picks the largest pile, 8, and Charlie takes the smallest pile, 1. In the second round, the remaining piles are 4, 2, 2. Again, Alice picks the second largest pile, which is 4, Bob picks the largest pile, which is 2, and Charlie takes the smallest pile, which is also 2. Following this strategy, Alice ends up with the piles 7 and 4. Adding Alice's coins together, we find that her total is 7 plus 4 equals 12. This value is returned as the output for this example. Let's look at another example. Here, the input is piles equals 9, 8, 7, 6, 5, 1, 2, 3, 4. First, we sort the piles in descending order, 9, 8, 7, 6, 5, 4, 3, 2, 1. Then, the game begins. In the first round, Alice picks the second largest pile, which is 8. Bob picks the largest pile, 9, and Charlie takes the smallest pile, 1. In the second round, the remaining piles are 7, 6, 5, 4, 3, 2. Alice picks the second largest pile, which is 6, Bob picks the largest pile, 7, and Charlie takes the smallest pile, 2. Finally, in the last round, the remaining piles are 5, 4, 3. Alice picks the second largest pile, which is 4, Bob picks the largest pile, 5, and Charlie takes the smallest pile, 3. Adding Alice's coins together, we find that her total is 8 plus 6 plus 4 equals 18. This value is returned as the output for this example. Now, let's consider a smaller case. If the input is piles equals 1, 2, 3, we first sort the piles in descending order, resulting in 3, 2, 1. In this case, Alice only gets one turn because there are just 3 piles. Alice picks the second largest pile, which is 2. Bob then picks the largest pile, which is 3, and Charlie takes the smallest pile, which is 1. Alice's total coins are simply 2. This value is returned as the output. Finally, let's consider the constraints for this problem. The number of piles is always at least 3 and at most 3 * 10^4, and the number of piles is guaranteed to be divisible by 3. Each pile contains between 1 and 10^4 coins. For edge cases, if there are exactly 3 piles, Alice can only pick the second largest pile. If all piles have the same number of coins, Alice's total will depend on always selecting the second pile in each group of 3. The solution must also handle large inputs efficiently, given the constraints. To begin, let's consider the brute force approach as an initial attempt to solve the problem. The intuition here is straightforward. Since we're distributing coins among Alice, Bob, and Charlie, we could generate all possible ways to split the piles into 3 groups and calculate the maximum coins Alice can collect based on the game's constraints. This involves simulating the process where each person takes their respective piles. Bob picks the largest pile, Alice the second largest, and Charlie the smallest. However, implementing this would require generating all permutations of the 3 n piles and evaluating each case. The computational cost of this method is extremely high, with a time complexity of 3n, making it infeasible for larger inputs. While it's a natural first step to explore, the brute force approach is simply not practical for real-world problem sizes due to its inefficiency. Now, let's discuss the greedy approach, which presents an optimized solution. The key insight here is that to maximize Alice's coins, we need to ensure she consistently gets the second largest pile in every round of selection. This can be systematically achieved by sorting the piles in descending order. Once sorted, Bob takes the largest pile, Alice takes the second largest, and Charlie takes the smallest in each group of 3. By iterating through the array and summing up every second pile, starting from index 1, for n steps, we can efficiently calculate Alice's total. The time complexity of this approach is dominated by the sorting step, which is O(3n) log 3n, while iterating through the sorted array adds just O(n), giving an overall complexity of O(3n) log 3n. This solution is not only efficient but also straightforward to implement. Alternatively, we could consider partitioning instead of sorting. Using a method such as quick select, we could directly isolate the n largest and 2n second largest piles, summing Alice's portion accordingly. While partitioning has an average complexity of O(3n), it introduces additional complexity in implementation, making it less appealing for practical purposes compared to sorting. The greedy approach emerges as the most suitable strategy for this problem. It strikes the right balance between simplicity and efficiency. By sorting the piles, we gain complete control over the order of distribution, which aligns perfectly with the game's rules. There are a few key observations to note. First, Alice's coins are maximized when she always takes the second largest pile in each group of 3. Second, sorting the piles ensures a deterministic and systematic way of assigning piles to each player, removing ambiguity. Lastly, iterating through the sorted list is both simple and intuitive, avoiding the pitfalls of more complex algorithms. While brute force is far too slow to be practical in partitioning, though faster, introduces unnecessary implementation complexity, the greedy approach offers a clear, efficient, and easy-to-understand solution. It is slightly slower than partitioning but significantly easier to debug and implement, making it the optimal choice for this problem. The problem we're solving here is about distributing a pile of coins among 3 players, Alice, Bob, and Charlie. Our goal is to maximize the number of coins Alice can collect while following certain constraints. Specifically, all 3 players must receive at least some coins, and the sum of their coins must equal the total pile. To start, we need to understand the input and constraints. The input is a pile of n coins, which could be as large as 10,000 coins. The key constraints require that Alice gets the maximum number of coins, while Bob and Charlie must each receive at least 1 coin. With these conditions in mind, the next step is to generate all possible distributions of the coins. Using a brute force method, we explore every way to split the pile into 3 groups. We define the coins received by Alice, Bob, and Charlie as A, B, and C, respectively. The constraints can then be expressed mathematically. A plus B plus C must equal the total n, and both B and C must be greater than 0. This sets the foundation for our algorithm. Now that we understand the constraints, the next step is to focus on maximizing Alice's share. To do this, we iterate over all possible values of B and C. We start with B equals 1 because Bob's share must be non-zero. For each value of B, we calculate the remaining coins as remaining equals NB. Then, we iterate over possible values of C, starting from 1, since Charlie's share also cannot be 0. For each pair of B and C, we compute Alice's share as A equals remaining C. We check if this calculated value of A is valid, meaning it must be greater than or equal to 0. Throughout this process, we keep track of the maximum value of what we've seen so far. To optimize the algorithm, we can stop iterating early whenever remaining C becomes negative. This avoids unnecessary calculations when the remaining pile cannot satisfy the constraints. Once all feasible distributions have been explored, the algorithm returns the maximum number of coins Alice can collect. From this process, we can draw some key insights. First, the brute force approach is feasible because the maximum number of iterations is proportional to the size of the pile, n. Specifically, the time complexity is O(n squared), as we explore all possible pairs of B and C. Second, the optimization with early stopping helps improve efficiency by skipping invalid cases where the constraints cannot be met. Third, analyzing edge cases is critical. For example, if the pile size n is less than 3, it's impossible to split the coins into 3 non-zero shares. When n is exactly 3, there's only one valid distribution, A equals 1, B equals 1, C equals 1. Regarding data structures, the problem is straightforward enough to only require simple variables for A, B, C, and max_A. This is because we're dealing with numerical calculations that don't involve complex relationships. Finally, iterative counters are used to systematically explore the distribution space, ensuring no valid combination is missed. To summarize, the algorithm has a time complexity of O(n squared) and a space complexity of O(1), making it efficient given the constraints of the problem. The problem requires maximizing the number of coins Alice can collect by adhering to the rules of coin distribution. The optimal solution involves leveraging the sorted order of the piles. ###explanation. 1. Sorting the piles. The first step is to sort the piles in descending order. This ensures that the largest coins are at the beginning of the list, making it easier to distribute coins optimally. 2. Iterating and picking coins. After sorting, Alice picks the second largest pile in each group of 3 coin piles, based on the rules of the distribution. The largest pile goes to Bob. The second largest pile goes to Alice. The smallest pile is removed, goes to Charlie. This process repeats for all groups of 3. 3. Skipping every third pile. By iterating over the indices where Alice's coins are located, every second pile in the sorted list, starting at index 1, the total coins Alice collects are calculated. For edge cases, the solution handles edge cases where the input size is minimal, e.g., 3 piles, or where all piles have identical values, as the sorting and iteration logic still correctly identifies Alice's portion. This implementation is efficient, with a time complexity of O(n log n) due to sorting in O(n) for the iteration, making it suitable for inputs up to the constraint of n equals 10 to the power of 4. This is the Java implementation for LeetCode problem number 1561, maximum number of coins you can get. The code mirrors the logic of the Python implementation, sorting the array and selecting the second highest piles in a group of 3. Java-specific differences include explicit type declarations, use of arrays.sort for sorting, and the absence of Python-specific constructs like list slicing. The iteration logic and mathematical approach remain consistent with the Python version. To solve this problem, we start by sorting the input piles in descending order. For the given input, 9, 8, 7, 6, 5, 1, the sorted piles become 9, 8, 7, 6, 5, 1. This ensures that the largest values are at the front, which is important for the strategy we'll use to maximize Alice's coins. Next, we initialize a variable total_coins to 0. This will keep track of the total number of coins Alice collects as we iterate through the appropriate indices. Using the formula range, 1, len, piles, // 3 by 2, 2, we determine the indices of the piles Alice will pick from. Here, with len, piles equal to 6, len, piles, // 3 evaluates to 2, and len, piles, // 3 asterisk 2 gives 4. So, the range becomes range, 1, 4, 2, meaning Alice picks from indices 1 and 3. In the first iteration, where I equals 1, we add piles, 1, which is 8, to total_coins. This brings the total to 8. In the second iteration, Alice picks from index 3 of the sorted piles. At this index, the value is 6, so we add that to total_coins. Adding 6 to the current total of 8 gives us a new total of 14. This concludes the iterations for this example, as the range only includes indices 1 and 3. Therefore, the maximum number of coins Alice can collect from this input is 14. We now move on to the next example, where the input piles are 2, 4, 1, 2, 7, 8. First, we sort these piles in descending order. After sorting, the piles become 8, 7, 4, 2, 2, 1. Once again, we initialize total_coins to 0 to track Alice's collected coins. Now, we determine the indices Alice will pick from using the same formula as before, range, 1, len, piles, // 3 by 2, 2. In this case, len, piles, is still 6, so the range evaluates to range, 1, 4, 2. This means Alice will pick from indices 1 and 3. In the first iteration, where I equals 1, we add the value at piles, 1, which is 7, to total underscore coins.
This brings the total to 7.
In the second iteration, Alice picks from index 3, where the value is 2.
Adding this to the current total of 7 gives a new total of 9.
Thus, for this example, Alice collects a maximum of 9 coins.
For the third example, the input piles are 1, 2, 3, 4, 5, 6, 7, 8, 9. After sorting these piles in descending order, we get 9, 8, 7, 6, 5, 4, 3, 2, 1.
As always, we initialize total underscore coins to 0. We then calculate the indices Alice will pick from using the formula range 1 len piles / 3 by 2 2. Here, len piles is 9, so len piles / 3 equals 3, and len piles / 3 * 2 evaluates to 6.
This gives us the range 1, 6, 2, meaning Alice will pick coins from indices 1, 3, and 5.
In the first iteration, where I equals 1, the value at piles 1 is 8.
Adding this to total underscore coins gives a total of 8.
In the second iteration, Alice picks from index 3 of the sorted piles, which has a value of 6.
Adding this to the current total of 8 results in a new total of 14.
In the third and final iteration, Alice picks from index 5, where the value is 4.
Adding this to the total brings the final sum to 18. Therefore, for this input, the maximum number of coins Alice can collect is 18.
This concludes the example, and we see how sorting the piles and strategically picking coins from specific indices ensures Alice collects the maximum possible total. To understand the time complexity of this algorithm, we break it down into 3 key steps.
First, the algorithm sorts the array of piles in descending order using Python's timsort algorithm.
This sorting operation has a time complexity of O n log n, where n is the size of the input array. Timsort is highly efficient because it works well with both partially sorted and completely unsorted data.
Next, we have the iteration step, where we loop through specific indices to pick the second largest pile in each group of 3. Since the loop runs for len piles divided by 3 iterations, this simplifies to O n, because constants are ignored in big O notation. Lastly, during each iteration, we add the selected pile's value to the total coins.
This addition is a constant time operation, O1, performed once per iteration. Combining these steps, the sorting operation dominates the runtime, meaning the overall time complexity of the algorithm is O n log n. Now looking at the space complexity, the primary consideration is the sorting operation. Python's timsort algorithm is an in-place sorting algorithm, which means it does not require additional memory proportional to the input size, resulting in O1 extra space. Beyond sorting, the algorithm uses a few variables, such as total underscore coins and the loop counter, to keep track of the result and iteration progress. These variables also require constant space, as they do not scale with the size of the input. Since no additional data structures or memory allocations are introduced, the overall space complexity of this algorithm is O1. This makes it highly efficient in terms of memory usage. To better understand the efficiency of this approach, we can compare it to a brute force or naive method. A naive solution might involve repeatedly finding the largest, second largest, and smallest piles within groups of 3, simulating the process manually. This would often require sorting the piles multiple times or maintaining a priority queue to extract elements, which could lead to a time complexity of O n squared, or O n log n, for each group. This approach is much less efficient than the current algorithm. The optimized algorithm, on the other hand, sorts the piles once and directly iterates over the relevant indices, avoiding redundant operations. As a result, it achieves the best possible time complexity of O n log n, making it significantly faster and more practical for large inputs. Finally, let's analyze the best and worst case scenarios for this algorithm. Even in the best case scenario, such as when the piles are already sorted in descending order, the algorithm still performs the sorting step. This means the time complexity remains O n log n, as sorting cannot be skipped. Similarly, in the worst case scenario, where the piles are in completely random order, the sorting step still has the same complexity, O n log n. The iteration step, which is O n, does not change based on input order. Hence, the time complexity is consistent across all cases. Mathematically, we can confirm this by noting that the sorting step dominates the runtime, contributing O, n asterisk log, n. Iterating over n/3 indices and summing coins are both linear operations, O, n, but these are overshadowed by the O, n asterisk log, n term. Therefore, the overall complexity simplifies to O, n asterisk log, n, regardless of input characteristics. One common mistake when tackling this problem is overcomplicating the brute force approach. Many candidates jump into optimization too early, adding layers of complexity before first solving the problem with a straightforward brute force solution. This wastes precious time and increases the likelihood of introducing bugs. It's better to start simple, then optimize. Another frequent error is ignoring edge cases. For example, you should test scenarios like having no coins at all coins being in a single pile, or even a pile that contains 0 coins. Overlooking these cases can lead to incorrect results or runtime errors, which can be costly during an interview. Lastly, incorrectly handling the division of piles is another pitfall. Many assume piles can always be evenly divided or forget to account for remainders, which leads to logical errors. Problems involving constraints like equal distribution or minimizing differences often require careful handling of these situations to avoid mistakes. Now, another issue is hard-coding values in your solution. If your code only works for specific input sizes or constraints, it's not flexible enough for dynamic inputs. Hard-coding demonstrates poor adaptability and could undermine your performance in an interview. Additionally, neglecting time complexity can be detrimental. While it's fine to start with a brute force approach, you must keep scalability in mind. If you fail to optimize for large constraints, it reflects poorly on your problem-solving skills. Knowing when to transition from brute force to a more efficient solution is an important skill to demonstrate during technical assessments. Always aim to balance simplicity with scalability. In interviews, recognizing patterns is key. Many distribution problems share common themes such as minimizing differences, balancing partitions, or maximizing certain outcomes. Carefully analyzing test cases can help you identify these patterns. Once you have a brute force solution, focus on optimization strategies. Techniques like dynamic programming, greedy algorithms, or prefix sums are often highly effective for distribution problems. Clear communication is also essential. Explain your thought process, starting with why you chose a brute force approach and how you plan to refine it. This shows structured problem solving. Flexibility is another important attribute to demonstrate. Consider potential variations, like uneven distributions, constraints on who receives coins, or additional goals such as minimizing variance. Finally, exploring related problems, like partition equal subset sum or coin change, can deepen your understanding and prepare you to tackle similar challenges. When it comes to alternative approaches, dynamic programming is a powerful technique. It allows you to track possible distributions or subset sums efficiently, making it ideal for problems involving sums or equal partitions. However, it does come with higher space complexity and can be tricky to implement under time pressure. Another approach is using a greedy algorithm. This involves making locally optimal choices, which is simple and fast for certain scenarios, like minimizing variance or maximizing a specific pile. The trade-off is that greedy algorithms might not always find the globally optimal solution. Backtracking with pruning is another option to consider. By exploring all possibilities and cutting off unviable paths early, you can guarantee correctness for smaller inputs. However, this method becomes inefficient for larger inputs unless combined with memoization to reduce redundant computations. Heuristic-based approaches offer another alternative. These methods rely on approximations or rules of thumb to arrive at a solution quickly. They are particularly useful when an exact solution is either unnecessary or infeasible due to time or resource constraints. The advantage of heuristics is their speed and simplicity, but the downside is that they don't always provide the best solution. These approaches are most effective in scenarios where a reasonable approximation is sufficient, and precision isn't a strict requirement. Understanding the trade-offs between these methods helps you choose the right strategy based on the problem's constraints and goals. Thanks for joining me in solving the maximum number of coins you can get problem. We reviewed the greedy approach, highlighted its efficiency, and discussed the importance of sorting in optimization problems. Don't forget to like, subscribe, and check out more solutions to sharpen your skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!